Last time we focused on describing how objects rotate and using things like the rotational kinematic equations to determine different aspects of rotational motion, like angular displacement, angular velocity, angular acceleration. But we didn't really talk about why objects rotate, and that's going to be the focus of today's lesson on a new concept for most of you called torque. So what exactly causes an object to start rotating if it is currently not? Well, let's think about, first off, just regular old acceleration. For linear motion, or regular side-to-side translational motion, forces cause objects to start moving if they are currently at rest. So it's a force which causes an acceleration. But what causes an angular acceleration or a start in rotational motion will instead be a torque. So let's say I have this wrench here, and I want this wrench to rotate around so that it will rotate this bolt. So our axis of rotation is going to be right here on this bolt. Well, I can rotate it by applying a torque. And a torque is, in essence, kind of a twist. If a force is a push or a pull, a torque is a twist around an axis of rotation. And we abbreviate torque with this new symbol here. This is a lowercase tau. It kind of looks like a curvy T. And this is a measure of how well a force causes an object to rotate. But it depends on a few different factors. First off, it depends on the size of the force. If I push harder, that's going to cause it to rotate more efficiently. So the size of the force is a factor of torque. But another factor is, where do we apply this force? So if I apply the force way out here at the edge, most of you know from experience that you're going to have more leverage, and I'm going to be able to make this wrench rotate much easier than if I instead applied a force right here, very, very close to the axis of rotation. And additionally, what also matters is the angle at which this force is being applied. So for instance, if I apply it pretty perpendicularly to this wrench, it's going to go pretty easily. But if instead I push inward toward the bolt, well, it's not going to rotate. It's just going to awkwardly sit there. Same thing if I pull it out, it's just going to pull the whole wrench off the bolt. That's not going to really work either. You have to be pushing it perpendicular to that wrench. The angle is important too. So let's start building an equation for torque, and I'm going to start off by kind of giving ourselves a little bit of a visualization here. So let's imagine that I've got this we'll say hinge here with something attached to it, like a rod that's going to spin around this hinge. So ultimately what I have is this is the axis of rotation right here. Now this axis could be an axle, could be a pivot. I said in this particular case it's going to be a hinge. And if I start to rotate this around, I can do that by applying a force to this bar. And what would the equation for the torque be here? Well, it's going to be tau is equal to Rf, where F is the magnitude of the force in newtons that I'm pushing with, and R is what is known as the length of the lever arm in meters. And the lever arm is specifically the distance between where you apply the force and the axis of rotation. So although this bar actually has a longer radius, if you will, it extends further out, the only part I care about is the part between where I apply the force and the axis of rotation. This here is the lever arm. So that length times that force gives me a torque, and the units of torque are Newton meters. Nothing more fancy than that. We just call it Newton meters. Now, one thing we have to keep in mind, though, is as we said earlier, this angle matters. It would be more efficient if I push it perpendicularly, because if I look at this force has two different components. It has a parallel component to it, and it has a perpendicular component to it. But the parallel component's not going to help me push the rod in a circle. The only thing that's going to help with that is the perpendicular component. And so we actually need to change this a little bit. We need to put F with this symbol for perpendicular, because this is really the force perpendicular to the lever arm. It doesn't matter how hard I push. If it's not perpendicular, the object is not going to rotate and the torque will not be properly applied. Now I can calculate this in a slightly different way by recognizing that this angle theta here, which is the angle between the force I apply and the lever arm, I can rewrite the equation as Rf sine theta, because the perpendicular piece of this force, which is essentially the same thing as this is the sine component of this angle. And so this angle theta is specifically the angle directly between this force and the lever arm. So we could either say tau is equal to RF perpendicular or it's equal to RF sine theta. As long as that angle is the one directly between the two, we should always get the same thing. So let's look at an example. Let's say we have a rod, and this rod is capable of rotating around an axle at its center. So let's kind of say this is like an overhead view, and it can rotate like this. And we want to determine the torque on the rod from each of these four different forces. So I've got force 1, force 2, force 3, and force 4, and these are applied at different distances. And feel free to go ahead and do this on your own to find each of these torques. This would be good practice, but I'm going to go ahead and jump in pretty quickly right now. Well, looking at the first one, my first one, which is pushed directly in the side here, well, that's actually just going to be a torque of 0. And why is that going to be a torque of 0? Well, there is no perpendicular component to this force. This force is going directly into the axis of rotation. So the angle between this and the lever arm would be 0 degrees, and sine of theta, where in this case this is 0 degrees, there we go, will be 0. So we should not be expecting a torque here. Well, let's look at the second one. Well, the second one, I'm going to have RF perpendicular, and my R is 0.25 meters. That's the length of the lever arm from the axis of rotation to the force. And to find that perpendicular part, I'm looking for this piece here, which is the same thing as F sine theta, and that theta is 30 degrees, the angle between the two. So I'm going to use my calculator and do 0.25 meters times 40 newtons times sine of 30 degrees, and I get a torque of 5 Newton meters. All right, now let's look at the third one. Well, if I look at the third one, I'm once again going to get a torque of 0. And I think a lot of you will recognize that because it's not going to cause the object to spin. Because the lever arm right here is just 0. I'm not applying it to one side or the other. I'm applying it instead directly at that axis. So the torque here would be 0 as well. And lastly, for the 4 force, I would get R4, F4 perpendicular, but this one is fully perpendicular, so I don't need to worry about any angle, so it's just going to be 0.2 meters times 2 newtons, or a torque of 2 Newton meters. But let's say we want to take it a step further, and let's say we want to know what is the net torque on this object. Well, you might be tempted to say, well, okay, 5 Newton meters, 2 Newton meters, 0 and 0, so it's going to be 7 Newton meters. And that's not quite correct. And the reason why is because the torque going this way from F2 and the torque going this way from F4 are going to be opposing each other. And so we need to start defining positives and negatives. And typically speaking, not always, but typically speaking, we define a positive torque if it makes the object go in a counterclockwise direction, and a negative torque if it makes it go in a clockwise direction. So in this particular case, the torque from F2 would be negative because it's going to cause this rod to go in a clockwise direction. So I'm going to say negative 5 Newton meters. And the torque from F4 I'm going to say is positive 2 Newton meters because it's going to cause it to go in a counterclockwise direction. So now if I find my net torque, I'm going to see that it's actually, just adding those together, negative 3 Newton meters. Or in other words, it is a clockwise torque. The rod is going to start going in a clockwise direction. Well, now that we've talked about how an object starts rotating, what's going to affect how quickly its rotation rate is going to increase, decrease, or whatever. And let's take that by going a step backwards. If I have an object and its motion changes, if it accelerates, what determines that change in motion? Well, a couple of different factors, and we define this using Newton's second law, which that second law tells us that if the forces on an object are unbalanced, if there's a net force, the object will accelerate with an acceleration directly proportional to the net force. So more force, it accelerates more, and inversely proportional to the object's mass. If the object has more mass, it accelerates less because it has more inertia, more resistance to that acceleration. And now let's redefine this in a rotational context. So instead of wanting to know how an object's motion changes, what determines how an object's rotation changes? In other words, what determines an object's angular acceleration rather than its linear acceleration? And that angular acceleration we abbreviate with alpha, and I'm literally going to rewrite, and you might want to do this below, a completely new, but not really, Newton's second law. This one's specifically for rotation. It looks exactly the same, but I've changed some of the terms to fit into a rotational context. If the torques on an object are unbalanced, like we saw in that last example, then the object will angularly accelerate. Its acceleration will either cause it to speed up its rotation, slow down, change direction, whatever. With the angular acceleration, it's going to be directly proportional to the net torque in Newton meters, and it's inversely proportional to the object's... Well, okay, well, what's it inversely proportional to? What about an object makes it resist angular acceleration or rotation, or changes in rotation, just like its mass causes it to resist changes in motion? Well, let's see if we can piece it together. So I have right here a disk, and that disk has some radius r, and it's going to start spinning. And when it spins, I'm going to basically cause that by applying a force here on the outside edge, which is going to cause it torque, allowing the disk to rotate. I'm going to be focusing specifically on this point right here. And if I'm looking at this point, when I apply this force, it's going to start accelerating with a tangential acceleration. It's going to start speeding up, and that's going to cause the entire disk to start rotating with some angular acceleration alpha. All right, well, let's look at Newton's second law here, because Newton's second law would still apply for this point here. The acceleration of this point would be the net force, which we'll go ahead and say is just this force right here, divided by the mass of that little point right there. Well, how can we redefine this in an angular context? Well, first, I'm going to divide both sides of this equation by r. Now, if I do that, what is the tangential acceleration divided by r? Well, that is just alpha. That's the angular acceleration, because remember, the alpha times r gives us that tangential acceleration. So now I have angular acceleration is equal to that force divided by the mass of that point times r, the radius that it is from the axis of rotation. Now let's do one more little mathematical trick. I'm going to multiply the top and the bottom of this right-hand side by r, which I can do. It's the same thing as multiplying by 1. And if I do that, I'm going to end up with f times r and mr times r. Well, f times r, keeping in mind that this f is perpendicular to this axis, that f times r is just a torque. And the bottom is going to be mr squared. And this is something new. Mr squared is a new value which we're going to abbreviate with I. And this is that resistance to rotational changes in motion. And this I, capital I, is something known as rotational inertia. And this is a property of an object that causes an object to resist changes in rotational motion, or in other words, resist angular acceleration, and must tend to maintain its current angular velocity. So if it's not moving, it's what causes it to resist the angular acceleration. And if it is spinning, that's what causes it to resist any changes in spin, whether it's going faster or slower. Now, rotational inertia is actually kind of a modern term. It has historically been called something else you're going to see a lot, especially if you look stuff up online or in your textbook, which is moment of inertia. Moment of inertia, that moment doesn't really stand for time. Really, it's just kind of a derivative of the word momentum. Moment of inertia is a very, very popular term still, so you need to keep in mind that these are the same thing. Rotational inertia, moment of inertia, they mean the same thing. And if I have a single point here on this disk, the rotational inertia of that point as it moves around is I is equal to mr squared, where I is the rotational inertia, m is the mass at that point in kilograms, and r is the distance between the axis of rotation and that point in meters. Now note, that's not the radius of the entire disk. If my point was instead here, it would be a smaller value for r, and that gives me a rotational inertia with units of kilograms meters squared. So the rotational inertia of a point, or its resistance, does not just depend on its mass. It also depends on the distance between that mass and the axis of rotation, which may be a little surprising. But you have to remember that points that are further out, well, they're moving faster as the object is rotating, so it's going to take more of an effort to slow them down than points that are closer to the axis of rotation. But this is an issue, though, that this is only telling me about the rotational inertia of this one point, but typically speaking, if I have a rotating object, I don't just care about one point on the object. I want to know about the entire object. So I want to know how this entire object resists angular acceleration. And we take this equation and we expand it into a bunch of different equations that kind of all have the same form for the rotational inertia of an entire object. And that form is going to be something like this, where I is equal to some fraction here, mr squared, where m is the entire mass of the object and r is the entire radius of the object. Now this fraction, okay, I know it looks like hashtag over hashtag. What I'm telling you here is that this is some numerical fraction. It could be 1 over 2, 2 over 3, 2 over 5, 3 over 7. I don't know. This fraction is particularly dependent on how is the mass distributed within the object? Because, for instance, if I have all of the mass concentrated on the edge, well, it's going to be harder to stop the object than if all of the mass is mainly concentrated at the middle with just a little bit on the edge. So how that mass is distributed affects its entire rotational inertia. And there are many, many different equations for this, and we're going to look at some of those now. I'm going to recommend what you do right now is you take your notes and you rotate them horizontally, because we're going to figure out the equations for many different types of rotating objects, looking at their mass distribution to figure out what their equation for the rotational inertia is. Now, you can go ahead and take the time to draw them all out. It's good to have this in your notes so you can quickly refer to them. But the good news is you do not need to memorize these equations. They will always be provided to you when you need them, particularly on assessments. Unlike a homework assignment or practice, you might need to go look it up, but on your exams or your tests, it will be provided to you. Additionally, you can go look them up online pretty easily. So let's go ahead and start with this object here, which this is a hoop or a ring that is spinning about its center. Now this, if you look, all of the mass is literally as far away from the axis of rotation as possible, so it's not surprising that the fraction here is literally just 1. That I is equal to mr squared, where m is the mass of the entire ring and r is the radius of that ring. But now let's take the mass and distribute it throughout that entire object here. And so we're going to now have a disk with the same mass as this ring, but all of the mass has been distributed through it. And so now we have I is equal to, and this is a disk or a cylinder spinning about this axis of rotation in the center, and I is now going to be equal to 1/2 mr squared. We have halved that rotational inertia. But now let's say we don't have something that's cylindrical in shape. Let's say something that looks like a ball or spherical. And let's say we have like a hollow sphere. So this is often called a spherical shell, where all the mass is concentrated around the outside of the sphere that is spinning about its center. And its fraction is going to be 2/3 mr squared. Now note it is less than this because we have some mass at the poles, very close to the axis of rotation, so closer than this, but it's not as efficient as this one when it's in a disk form. The next one we're going to have is, let's say we take that sphere, but we distribute the mass throughout the sphere. So this is a solid sphere spinning about its center, and I is now going to be 2/5 mr squared. So now we're going to take this a step further, and we're going to say, all right, well, what happens if we have something that's like a rod? Like, for instance, this. And if I take that rod and I spin it about its center, about a central point, we're going to get something that looks like this. And notice that this is the mass of the rod, and this L here, this is a lowercase cursive L, is the entire length of the rod. It's not the radius, it's the entire length. If it's spinning about its center, this is going to be 1/12 ml squared. And lastly, we're going to take a thin rod, and we're going to instead spin it around one end, so that would be like spinning it like this, rather than around the center. And we're still going to have M and L, but this is going to be 1/3. Now you might be wondering, why haven't we taken the time to talk about where these fractions come from, and why aren't we finding them ourselves? Well, the reason why is to figure these out, you actually have to use calculus. You have to basically integrate these masses over 3D objects, and we're not going to do that here. What you need to do is be able to look up these equations when you need to calculate them, but you also need to be able to conceptually think about, okay, is the mass closer to the axis of rotation or further away, and therefore the rotational inertia should be smaller or bigger, depending. We want to be able to conceptually think about it in that way. So going back to Newton's second law for rotation, I'm now just going to fill in one last piece, which is that the angular acceleration of this object is inversely proportional to the rotational inertia of that object, or capital I, where the rotational inertia is kilograms meters squared. Those are the units. All right, so let's look at another practice problem. Let's say we once again have a rod, and we'll say this rod is specifically rotated in a vertical circle around some central axle. So it's basically going this way. And we want to determine its angular acceleration when this one provided force applies a net torque to this rod. Well, how exactly would we go about doing this? We would start off by thinking about, okay, well, Newton's second law for rotation, or alpha, is equal to the net torque over I, the rotational inertia. Now let's start plugging in some values. Well, the net torque, thankfully for us, we only have one force here, so it's going to be the length of the lever arm times this force perpendicular. It is perpendicular, so there's no sine or theta here. And for the rotational inertia, this is a rod spinning about its center, so I'd go to my table of equations, I would look that up, and I would go, oh, okay, the equation is 1/12 ml squared, where L is the entire length. I should really make that a There you go. So it matches the table. ml squared, where L is the entire length of that rod. And let's just start sticking in numbers. The length of the lever arm is 1.5 meters. The force is 12 newtons, and this is going to be positive because it's going to cause the object to go in the counterclockwise direction. And then the bottom, we have 1/12. The mass is 2 kilograms, and the entire length, well, half of it is 1.5 meters. The entire length is 3 meters squared. I'll plug this in my calculator, and I get a value of 12 radians per second squared. Or in other words, this object is going to start angularly accelerating at a rate of 12 radians per second squared in the counterclockwise direction. And with that alpha, I could, figure out, well, how far is it rotated, or how quickly is it rotating its angular velocity, by starting to use those rotational kinematic equations. But let's say we took this same 3-meter long rod that was still 2 kilograms in mass, and we're now moving the axis to one end of it, and we're going to move it in a vertical circle this way rather than from the center. And we want to determine how big of a force is necessary to give it the same angular acceleration of 12 radians per second squared. Now the first part of this is going to be pretty simple. I'm just going to once again use Newton's second law for rotation, where alpha is equal to net torque over I, and I'm going to rearrange it because I want the net torque now is equal to the rotational inertia times the angular acceleration. But I already know the angular acceleration, and I can figure out I, the rotational inertia, by looking back at my table. It's no longer 1/12 now it is 1/3, because it is from one end rather than through the middle. I plug all those numbers in, and I get a positive torque of 72 Newton meters. And at this point, you're probably thinking, okay, well, that's pretty easy. Then I just use the length of the lever arm, and I can figure out what the torque is from that force. And that would actually be incorrect, because there's one thing we're forgetting here, which is that as I am moving this, is my force the only force affecting this rod? Well, no, this rod also has gravity on it. And where is that gravity going to be applied? Well, it's actually going to be applied at the center of mass of the object, which if this rod is uniform will be at the center of the object. But that means that gravity is going to be applying a torque downwards. It's going to try and keep this rod, it's going to try to cause it to rotate in the opposite direction. So I need to not only consider the torque I'm applying, but also the torque due to gravity. So now to figure out the force I'm applying F, well, the net torque was positive 72 Newton meters. There's now two torques, and one of them will be RF for my force, and one is RF for the gravitational force. And those lever arms are different. Mine is the entire 3 meters. The force of gravity is only 1.5 meters. But I know that force of gravity, because that force of gravity is going to be 20 newtons, because it's 2 kilograms times 10 meters per second squared. Now, why did I make this negative? That's because that force is going to cause it to go in the clockwise direction. So if I do that, though, okay, I've got 72. I have 1.5 times negative 20, so 1.5 times 20, this would be negative 30. I add 30 across, and I get 102 Newton meters equals 3 times F, where my force is actually going to have to be 34 newtons to cause this to happen. So to get this angular acceleration and be overcoming the torque that is supplied by gravity, I have to push with a force of 34 newtons at this end of the rod. But this is probably pretty confusing, because why did we care about gravity, or the force due to gravity, when we pushed at one end, compared to when we pushed in the center? When we dealt with the center situation, I didn't care about the force of gravity on this rod at all. So why did that matter? Well, it has to come down to this, that the force of gravity we can always assume is applied at the center of mass of the object. And this is otherwise known as the center of gravity. So that's going to be at the center of this rod, or in other words, that will be right here at this position in that earlier situation. But if you look at that, that force is not going to be applying a torque, because it is at the axis of rotation. That lever arm here is just 0, so the torque due to gravity in this particular one is 0. So I didn't need to worry about it there. So this is very, very important. When our axis of rotation is at the center of gravity, we don't need to worry about the torque due to gravity. But when it's not, well, then we probably need to make sure we consider that. So this is going to be something we always want to check. Is there a torque due to gravity or not? And it really comes down to, is the center of gravity at the axis of rotation or not. We're actually going to learn it's a little more complicated than that, but right now that should be enough for the moment. So what are our main takeaways on this lesson about torque? One, can we identify the factors that a torque depends on, such as the size of the force, the length of the lever arm, and the angle that we're pushing at, and can we use those to calculate its magnitude? Can we determine the net torque on an object, keeping in mind the positives and negatives from clockwise and counterclockwise, and additionally, do we need to be considering a torque due to gravity? Remember, if the axis of rotation is the center of mass of the object, that's not an issue, but if it's not, we need to consider it then. Can we identify the factors that the rotational inertia of an object depends on, specifically its mass and the distance that mass is from the axis of rotation? And can we find the correct equation for a particular object and plug in the appropriate numbers to figure out what that value is? And lastly, can we utilize Newton's second law for rotation, specifically alpha is equal to net torque over the rotational inertia, to calculate an object's angular acceleration and find out, is it starting to rotate, stopping, rotate, speeding up, slowing down, etc.